However, this number, most of the time, it's not 0.9, right? But the thing is with compression, the phi factor is 0.9. So why do we consider it like that? Why do we usually say something lower? Let's say 0.5.
To be conservative.
But about what?
Weaker in compression than it is in tension.
That's generally true. That's generally true. Like steel would be weaker in compression than tension. But
Wait, no, that's not true, is it?
well, in terms of material, it's the same, isn't it?
Yeah.
So whether you have Fy here, Fy here, yeah. But what about steel members generally causes failure in compression?
Buckling versus the local buckling? Bending?
Yes, but let's just focus on Euler buckling, right? So what is it about I-beams and you know like the majority of steel sections that's different to, let's say, a stubby concrete column?
The flanges.
The fact that steel sections are usually really slender, right? Let's just draw it like that because that's actually more accurate. The cross section is usually really thin for how long it is. Makes sense. So that means it's prone to buckling, and that's a compressive. That's a result of compressive action or flexural action, right? So we're trying to use these really thin little amounts of steel because steel is really heavy. It's really expensive. We want to minimize the amount of steel we're using, right? So we use these really thin sections of steel essentially for how long they are technically. Because if you think about a concrete column or whatever, it's usually quite fucking wide and stuff compared to it, right?
Mm-hmm.
Yeah. Okay. That's why this number has to be lower. And again, it was like you said, Ken, it was to do with Euler buckling, right? We're accounting for Euler buckling. So essentially, let's just say N star C has to be less than phi NS, I think it was called. Do you guys remember these? Yeah. Do you remember the formulas for them?
NS.
Yeah, for NS. So wait, firstly, what is NS?
NS is section capacity.
Compressive capacity, yeah.
Yeah.
Okay, so do you remember the formula? It's like fucking KF is the form factor, right?
Okay, yeah.
That's it, right? So it's very similar to tension, except the form factors involved now, right? To account for local buckling. But let's just say we have form factors of sections that are like, they're not going to locally buckle. So let's just say KF is 1, okay? Where was I going with this? Okay, then it's fairly similar with to tension. Okay, sure. So the thing is about these two things, right? NS and NB. NB was, does anyone remember? Do you remember what NB was?
Is that like the compression? Like the full compression?
So NS was the section compressive capacity?
Because I think it's been denoted as NC before.
Oh, sorry. No, yeah, you're right. It is NC. I was testing you.
That's the full member
Yep.
compression.
Yep. And so, which one's going to be bigger? NS or NC?
NS.
Why?
Because NC is a function of NS.
So do you reckon it's that? Is that what you would say for this mathematical expression? NC is greater than NS?
No, NS is greater than NC.
Oh, sorry. I was testing you. So is it NC is less than NS as a hard rule?
Not as a hard rule. I think it depends on the slenderness, right?
Less
Yes.
than or equal to.
Exactly.
The
So
slenderness ratio.
this is correct now. So the member capacity always has to be equal to or less than the section capacity. We always calculate the section capacity first, and it can only ever get worse because of slenderness. Make sense?
Mhm.
Okay. So let's dive into what makes NC NC. The other thing is alpha C, right? And then again, it was a function of NS, right? This one on the right. So NC, that means NC can only ever be 1 or less than 1, right? Has to be 1, yeah, whatever. I don't fucking care about the capacity equation. I mean, like the inequality or whatever. So essentially we have this reduction factor like we did for tension, right? The exact same one, 0.9. But now we have another reduction factor stacked on top of that, right? We have alpha C. Alpha C is your slenderness reduction factor. So what determines alpha C? What are
B.
Yeah, that's true. Alpha B. But alpha B has a relatively minor effect, actually, because this is to do with whether it's hot rolled or like hot rolled will have a certain number, heavily welded HW will have a different number, but it only affects, if you remember like the curve, it only affects the number slightly. What matters more is actually this. This is the modified slenderness ratio, right? 1 second, it's coming to me. It's LE on R, and it's like, fuck. It's like KT root FY on 250 or something. I don't know, I could have butchered that slightly, but like these are the things that it roughly involved, right? Okay, maybe this equation, don't copy that in case it's wrong, but it's a function of a few things, right? It's a function of your effective length, it's a function of your radius of gyration, it's a function of KT, and KT is your form factor, so that's like how likely it is to locally buckle, and then like Fy, which is like steel material yield. The thing is, these two parts of the equation don't affect the outcome too much. KT and Fy don't affect it too much. What matters the most is your effective length, right? And what matters the second most is your radius of gyration. Okay? So what I'm trying to say is if you have a column like this, right? Let's say it's a square column, and you're applying like an axial load to it like this. The longer it gets, the more likely it is to buckle. Do we agree with that?
Mm-hmm.
Yeah. So that's your effective length. So what if it's like secured in both directions in the middle? The length of the column, let's say it's like 7 meters, but your effective length is just halved. Right. Instead of buckling like C shape, it's going to buckle like 2 C shapes. That's what we were saying last time.
Mm-hmm.
So effective length is the biggest factor, right? Agree?
Even bigger than radius of gyration.
So that's what I'll say next. So radius of gyration. Let's draw this as an I-beam because I think it'll make more sense. So say you have like an I-beam or an I-column or something now, right? We remember the major and minor axis directions, right? So what's this way?
That's the major axis.
That's major axis, right? That means it's better at bending along that axis. That's like the strong way. Right?
Oh.
Yeah, yeah. So like as in bending, so it does that. Did I draw that right? You know what I mean?
It's more resistant that way.
Exactly. To buckling. Because buckling is effectively a form of bending, right?
Like it's more resistant to buckling this way.
Yes. Because it's on its major axis.
In I direction.
What matters actually is the radius of gyration. So Rx is high. Because remember Rx is your square root moment of inertia over area. So basically we know that the I-beam is min-maxed so that Ix is really high, right? Which means that Rx is really high. Right?
So you say if I push it like along that axis, then
Yep,
you're
like that way.
forced to push it that way
Yes.
than the other way.
Yes.
Oh, really?
Yeah, because think about, okay, sorry, this is kind of getting random, but like say I have a plank of wood, like a 2x4, and it's much wider in one direction than the other, right? And I'm trying to and pretend like we're trying to cross a river or some shit,
Yeah.
and then I'm here. Is this way more likely to sag and bend and
Yes.
break than if I tipped it the other way?
Yes.
Exactly, right? So this is the minor axis for the piece of wood. So the major axis would be the other way, conversely, if I stood on it like... Sorry, I'm not drawing this very well. If I stood on the piece of wood that way, obviously it'd be wobbly, but it'd be really strong,
Yeah.
bending-wise, right?
Yeah.
That is basically what your I-beam in the major direction looks like.
Oh.
Your I-beam is basically doing that.
Oh, okay. I just thought it would be the other way around, but it's okay.
That's your I-beams stronger direction. Okay. So conversely, if we bent it along the y-axis, that way, right?
So that's the major axis.
This is the minor axis now.
But it's more likely to bend that way, right?
That's
That
like
means
if
it's
you're
minor.
standing inside of the channel.
Major axis means the direction with stronger bending resistance,
Oh, okay.
because it's the main way it's supposed to be orientated.
So it's not gonna bend that way as much.
Yes.
Okay.
Okay, so now minor axis buckling, right, is like the same thing as if this plank of wood was face down, right? Like that, that's essentially what we have. That's like if the I-beam was like sideways. It's not very good that way, right? What does that say about RY? Is it high or low for an I-beam? It's relatively low, right? Which means its radius of gyration is low, which means it's not going to reduce, sorry, the slenderness will be higher, right? This number here, the higher it is, the worse it is for buckling. Right. I'll give you some numbers. So if I go back to my email here, I was just talking to DeepSeek a bit today. Yeah, the first point here is about RY and RX. So if you're talking about a I-beam, RY is gonna be smaller than RX, like significantly, right? In the ballpark of like 10 times smaller than RX, right? So as the modified slenderness ratio increases, right, the capacity lost due to buckling becomes more pronounced, right? So when you get numbers around like slenderness, modified slenderness is 66, you're gonna lose about 20% of your member capacity, right? If you start getting numbers like 130, the capacity loss gets up to like 65%. So remember, your modified slenderness ratio is your effective length, so how long it is. Longer, the worse it is. And reduced lower radius of gyration, the worse it is. The bigger this number gets, the worse it gets, essentially, right? Make sense? So let's just look at an example. So this is from the Little Red Book, okay? And again, this is in the Google Drive. If you guys don't know where that is, Sigma Lectures link tree, and go to Steel's Drive, it's in there. So if you go to the compression section, and then look at universal beams, right, and say grade 300, here's buckling about the x-axis, right? We have some numbers. Let's just say whatever you calculated was that top one, 200 UB, 29.8, right? This, sorry? Oh, we're talking about compression. I just want to illustrate. Yeah. So let's say you get 1,100 capacity. So this is like phi ns. So when effective length is 0, that's just saying this is like your section capacity, essentially, right? And then as the length gets longer, we're factoring in like member capacity. Am I making sense? I feel like I'm not making sense. But like, so we're starting at numbers like 1,000, right? So this thing can take on 1,000 when we don't account for any buckling length, right? If this is like restrained against buckling the whole time, we essentially have an effective length of 0, right? As we get higher and higher, so this first row is 2, this first column is 2, then 4, then 6. Do you see how it decreases? So it goes from 1,100 to 1,050 at 2 meters. 4 meters decreases. 6 meters, it's lost like 30%. 8 meters, it's lost like 50%.
Yeah.
Do you see how it's like an exponential effect as you get longer and longer for effective length? That's what the modified slenderness ratio does. Anyway, sorry, circling back. Can you guys tell in the recording that my internet is fucking better? I guess you gotta fucking... Anyway, my point is, that's why I'm saying 0.5 is a good guess. Considering your effective length was 6, right, roughly?
Yeah.
Wait, can you repeat that?
So like, if you were to be more specific, would you interpolate the results and then?
Oh, so you don't actually do it through this table. This table is to give you a good idea of how to do it. This is how I would do it at work. But this saves you from doing all the hand calcs. There's 0 hand calcs using this table. He
Yeah.
wants you to do the hand calcs as you're learning it in uni. The slow way. But this is the fast way to quickly get a bunch of numbers. Do you see what I mean? So if we had an effective length that was longer, right? Say this became like 9 meters. What number would you use here instead of 0.5 as your initial guess?
0.3.
Yeah, like 0.2, 0.3 would be pretty safe. Would definitely pass. What if this length was 2 meters? What would you use?
It's like 0.8.
Yeah, pretty high. Do you see how it loses a lot over a longer span? That's what I'm trying to tell you. And the other thing is, in your assignment, it says, let's see if I can find it. This has basically just become an assignment. Yeah, not really. It says all members have a midpoint restraint buckling out of plane. That refers to, like, that only really matters for compression, right? Because tension, it doesn't matter. And what that's saying is halve the effective length in the minor axis. What it's saying is in the major axis, LEX is, what was it, like 6 meters roughly?
Actually, no. For this assignment, it's roughly about like 3-ish or 4-ish because
Okay.
it's for that number. But you can keep going.
Oh yeah, let's say it's 6 meters, right? But then LEY, if it was, if out of plane buckling, which means in and out of the page, which means minor axis, right? It, right? It has a midpoint restraint. You can pretend that your effective length is halved. Well, you don't pretend. That's actually what happens.
Right.
It's stopped its buckling effects out of
Yeah.
plane.
Okay.
But now say you have an I-beam, right? So you have an I-beam, and you're using Rx, which is high for an I-beam, but then you have this long length of 6 meters.
Okay.
But now you also have the same I-beam, but its Ry value is low because it's the minor axis and it doesn't really love buckling out of plane. But now you have this halved restraint at 3 meters.
Okay.
Which one's worse?
The top one.
Are you sure? But Ry is much lower than Rx, right?
But you're not going to be like it's not going to be used in the minor axis and stuff, is it?
It's not going to be used. But we're doing compression. We're doing this buckling effect. It can bend either way. It can bend in minor axis or major axis. You have to check for both.
Okay.
Do you see what I mean?
Mm.
So let's actually check it right now because I've prepared this example. So here we're looking at x-axis. This is major axis, right? At 6 meters. The top one, the capacity is 767. Keep that in mind. Okay, same one. But the halfway point, the minor axis is supported. So we're looking at 3 meters now instead of 6 meters.
Okay.
Now it's 547. That's lower than 747, right? So actually it's still going to buckle in the minor direction, more like first before it buckles in the major direction. Because Ry is so much lower than Rx for UB. Does that make sense?
Uh-huh.
So you should check for both. But the best thing you can do is follow my week 2 Yap. Oh, you know what I was going to do at the start? I was going to run over changes. No, I'll do that in recording separately. The best thing you can do is do this, where you have, this is the modified slenderness ratio, and it's the max between your x direction and y direction. And you check which one's bigger first before you continue your calculations for alpha C. So you don't have 2 separate capacity values. You just take the max of those 2 slenderness ratios and take whichever alpha C value you get. Am I starting to make no sense now? Do you guys have questions or not?
Can we just quote the little red book in finals and assignments?
Sir?
Can you quote the red book?
No. Well, you can reference it in terms of like to see if your number's in the right ballpark, but he wants to see you do hand calcs, right? That's the whole
But if
point.
we're
of
just
this one.
guessing for initial sizing,
Oh yeah, you can look at the red book and be like,
let's just guess 0.5.
yeah, you can, yeah. Yeah, you can work backwards, with the little red book and find the perfect initial sizing value. And then you don't have to redo it if it fucking fails or
Right,
something
right.
like that. Yeah. Makes sense?
Show that you're smart.
Okay, since we haven't really gotten into
Wait,
the
so
actual
is
Yap.
Compression design all about trial and error? Is that what you're trying to say?
Well, they're all kind of about trial and error, but like I'm trying to give you the best judge of trial and error. If you understand alpha C and you understand, if you understand why we chose this number here at the top, 0.5, 0.9 or whatever, you're not going to fail the check in terms of being like too low or too high, if you understand it properly.
Okay.
Make sense?
Uh-huh.
Okay. Yeah, and basically you just want to make sure it passes. And I think Caden, you were the one who asked if n star C, for example, is like 1,000 kilonewtons, right? And then the value you get, NC, right? Yeah, NC is the one for member, right? If your value is like 1,001, technically it's fine. And also if it's 1,000, I would say like 400 max, maybe 500 if it's really generous. That's also okay. I'd say anywhere in the ballpark of 0.1% over to 50% over is technically fine. Obviously, the best case scenario is if this is like 1,100, because then you're safely over. Yeah, and so it's safe, but you're not wasting too much material. That's like best case scenario. But he's gonna let you do this for this assignment either way. And the reason is it depends on the stage of design you're at. So when you're doing this at work, whatever, it's like, if it's an early stage design, you kind of want it to be generous in case like the fucking architect moves moves some shit around, and then you don't have to resize your members. Then it still passes the check. But if it's like a later stage in design, you kind of want to get it tight, if possible. Like detailed design. Makes sense, kind of. I feel like I'm starting to speak a different fucking language.
No.
Okay, no, it's good then. Okay, good. Okay, so this week, I'll kind of go over the gamma method quickly now, because it's not gonna matter to you guys until beam columns. It comes back in beam columns. That's why you gotta care about it. So, do you remember last week how we talked about effective length and we had this table, right? The thing is, in reality, it's not just going to be these numbers. It's not going to be 0.7, it's not going to be 0.85, it's not going to be 1 all the time. These are simplified numbers, right? We want a consistent way in order to find the perfect number to represent our stiffness, basically. It's all about stiffness in our column or whatever, right? That's what gamma method is, okay? Don't let this fuck up your brain. But basically we're looking at an entire frame, right? And all we care about is designing a single column essentially in this frame. That's usually how the question is worded. And how stiff it is, right? So whether, it's better represented by pin supports at the top and bottom, or better represented by rigid supports at the top and bottom, or like some combination, is based on the stiffness of the beams that is connected to it and the columns above and below it. So it's kind of like, it's like a spider web, right, of members. And whatever it's connected to is going to give it rigidity on the top and bottom. Is that an okay way to, do you guys get that? Sue? Okay. And so, how are we going to do that? Okay. So I know this is like kind of mindfucky if this is the first time you're seeing it. Top left here, this is top-down view, right? So like let's not look at anything else right now. This is just literally a top-down view of this 3D building that we're looking at, right? What do you guys reckon this is? So do you see how it's pointed and it says like B2? Oh yeah, that's right. Yeah, so we're on axis B and 2. This helps if you've done BIM or like the Revit course, because then you can start seeing how like sections and stuff come into engineering drawings. Yeah, but that at that intersection we have B2. We're referring to the column, but do you see how it's a H? What is that?
It's like a universal column.
It's a universal column. Yeah.
Mm-hmm.
And so now we're gonna start thinking about the direction the building is gonna bend essentially, and whether we're looking at something that's gonna bend in the minor axis or the major axis, depending on the view of it.
The whole building.
Yeah.
Okay.
So do you see how I've drawn like the blue? So it says frame 2 and 3, right? Referring to the Revit like section cuts like 2 and 3.
Yeah.
Frame 2 and 3 is what I've done in blue here.
Mm-hmm.
And I've kind of spoiled it. is it going to be doing major or minor axis bending? Sorry.
Minor.
Why?
Major.
Oh wait. Yeah, major.
Reaction.
Actually, I should say sorry. It's minor.
What?
I should be talking about it in terms of. Sorry.
Wait, which way is the force coming from?
Sideways, I should probably say.
the left
That's why.
to
That's why.
right.
It's like a lateral force.
Left to right.
Yeah, because it's about how much it will sway and shit.
So wouldn't it be? Oh yeah, it would be.
It is minor. Yeah.
What?
Okay. Basically, if you stare at it long enough, you'll kind of get it. But like, I don't want to spend too long on this. Another thing I want to show you is, do you see how orange is frame 1 and 4? Do you see how the blue and orange are like laid out?
Yeah.
1 and 4 are just the outer layers, right? Like the outer. But what it's saying is that they're braced in the middle.
Okay.
So frame 1 and 4 are braced, but 2 and 3 are sway columns. Sway frames. That's what it's trying to say. And then the other direction, it's swaying as well. But that one's x bending. Anyway, sorry. Like this is just context. That's how to read the drawings. Okay. So what I'm trying to say here is, remember what we did for compression design. This is essentially it in a nutshell, right? So this is what we covered last week. All that gamma method does is help you find LE. That's the only part of it that we're going to change here. In fact, specifically, it's going to help you find KE. Okay? Because remember, KE was from that table. It's either like 0.7, 0.85, 1, or whatever number. Now, here's a more accurate way of finding it, right? So, what you got to do is for the beams, right? So again, not again. This is the first time I'm saying it. We're focusing on this column, let's say. And this is just a part, sorry. We're looking at this from elevation view, right? So essentially, actually it's better if I just do this. Here's a side view of a column, of like a column system or something, right? A frame, I should fucking say. God, I can't speak. We care about this column specifically, the ground floor column 2, let's say, right? So now we do a zoom in of it, right? So I'm going to draw this out. And it's attached to the ground rigidly, let's say. What we care about is its fixity at the bottom, the beams that's connected to it, and the column above it. Okay? That's like the information we care about. So, which ones are the beams? Let's just do a quick check to make sure we're on the same
These are
page.
the horizontal ones.
That's one beam, that's another beam. Okay, what's the column above? That's that one, right?
Yeah.
Yes!
Yeah.
Yeah.
And so what we're saying is we have to find Ix for the beams. Because are the beams going to be bending in the major or minor axis when we're considering its swaying? This shit. If it does this, is it going to be minor or major?
Right.
So beams, which way are beams orientated for I-beams, let's say? Is it going to look like this and then go sideways? Or is it
Yeah,
going to look like this?
that. Number 1.
Is it ever going to look like the one on the right?
Not really. No.
It's never worth it to put a beam sideways for an I-beam or whatever. So we only care about major axis bending for beams. Make sense? Now the thing is for columns is they can be orientated like... I'm not drawing this very well. Like that, or like that, depending on whether we were looking at the east-west elevation or the north-south elevation.
Uh-huh.
So for the north-south elevation, we would care about the column's IY value, right?
Okay.
And for the east-west direction, and this isn't always the case, by the way. It's only the case because of how it's laid out here. So if these were oriented like this, it would be the other way around, right? Fine. But here we care about the XX bending of the columns. Anyway, what I'm trying to say is that's why we care about all these values. We care about the X direction and the Y direction for the columns. Because it's gonna... Yeah, we just might as well pluck all these numbers out of one deal.
Okay.
Yeah?
Yeah.
Okay. Okay, so we're gonna run through what an example looks like, okay? So the first step was just to note down all the values from one steel of those things. Now column loading. Let's just I've kind of spoiled this already. If you were given this apparatus and we're like, okay, find, did I just say column 2? Frame 3. Sorry, one sec. Oh, sorry, this is just an example. Okay, basically, the column on the left, right? We care about what axial loads this is taking. So how would we find that in this example?
Just using load factors, and then.
Yeah, okay, that's true. So let's say these are all loaded, like they're all factored. What do we do using this information to find the force going into column 2?
Just
Column
solve
2 is
the
it?
truss.
It's not a truss though. That's the thing.
Oh.
It's a frame. So how can we find the force there?
Reaction force.
Kind of. I mean, like, let's just say this, right? Pretend that top part is simply supported.
Mm-hmm.
How much of the load goes into the left and right?
W star times length over 5.
So half, right? So half the load goes here, half the load goes there, right?
Uh-huh.
Okay, so now, if I wanted to find the force in this column, it was just half of whatever loads were on top, right?
Mm-hmm.
Okay, what about the next level? Say I wanted to find the force in this column.
It would be the forces on top plus the ones that are being exerted on it.
Exactly. So we're getting more and more force as we go down, right? And so by this column, all we're doing is we're adding up the forces and considering half of the, it's called the tributary width.
Yeah.
Tributary just means like how much area or width is taking load. So it usually goes half and half if it's like uniformly distributed.
Yeah.
Yeah.
Uh-huh.
And so whatever reaction we get at the bottom here, that's n star c in that column. Do you know what I mean?
Yeah.
Because Newton's
Is
like
it
equal and
different from
opposite.
column 1 to column 2, or is...
It would be if there was extra loading here.
In that case, it would just be half of that one plus
Yeah,
one
yeah.
two column.
But these are the same because the loads here are the same as the loads here.
Okay.
Yeah. So this is kind of just how loads stack down in a building essentially, right?
Yeah.
Okay. Once you've found n star c, we use gamma method, right, to find ke. And now we've got this whole frame, and we need to find like the stiffness and stuff. Okay, let's see how it actually plays in. So here's our scenario. So it's very similar to what I drew before, right? At the bottom we have a rigid footing, right? And then at the top we have another column that goes up, and we have two beams coming off the side. So we need to see how rigid that whole system is. Here's the formula. So don't let this fuck with your head too much. What we need is we need a gamma value for the top of the column and the bottom. So what I mean is, do you remember how in that picture we had before? In that picture we had before, it was like stuff like this. You know, we have a pin support on the top and bottom. We have a rigid support on the top and bottom, stuff like that. So what we're saying with the gamma method is how rigid is each side, the top and the bottom of our column. So we need a gamma t value and a gamma b. Do you want to guess what that means?
Gamma column, gamma beam.
No, actually, because it's gamma t. Sorry,
Okay.
gamma t, gamma b.
Tension and beam.
One gamma value is for the top and one gamma value is for the bottom.
serious?
That's all it is. So that's why you need two gamma values, right?
No, I'm gonna...
But that's fine because usually most of the questions you're gonna get are ground columns, and the thing about ground columns is it's incredibly easy to find the gamma value for a footing, right? Because for a footing, it can only ever be this or this. So what I'm saying by footing is this is literally connected to the ground.
Uh-huh.
Gamma B, right?
Will they ever give it like in the middle of the frame?
Sometimes. But gamma B is simply 0.6 if your footing is rigid and 10 if your footing is pinned. That's like a hard rule.
Okay.
So basically if you're given a ground level column, one of the values is already given to you. So all the difficulty comes in finding gamma t, which is the top part, which is right here, because then you have to consider everything that's like spider webbing off of it, right? Okay, that's what this formula is. Gamma is the sum of I, right, which is the bending resistance, right, of each part, over L, and the top part is a column and the bottom part's a beam. Okay. And for beams, we only ever care about IX, right? Because again, beams are only ever orientated in the major axis direction. But
Are braces included in this formula?
Yes, because our modifying factor for the beam, right? So this is beta E. That's on the bottom part of the formula. That will change whether you have based on whether you have a braced or a sway member.
Okay.
Yeah.
Yeah.
So yeah, it's kind of inbuilt in the formula.
So like the angle at which it's braced at doesn't matter, right?
Oh, no. Because the bracing, you're assuming that it just can resist lateral forces and then transfer those forces into the ground. That's its only function. Yeah. Like wind, like it carries those forces into the ground. Whereas sway frames can't. So either it's braced or it's not. There's nothing really in between. Yeah. Anyway, so now and another thing that affects it is this table. So what you actually, alongside beta E, whether you have a sway frame or a brace frame, your KE you're gonna get from a different graph. Okay. So the thing is, for brace members, KE is always less than or equal to 1. For sway members, it's always greater than or equal to 1.
Okay.
So what does that say about KE? Does KE make your column stronger or weaker?
KE makes your columns weaker.
Yeah.
The higher it is.
Pretty much. And when we tie this back into LE, right? Because LE is your length times KE. What does that mean about your effective length?
It means that if your effective length is getting bigger, that means it's weaker. 'Cause it's
Exactly. Yeah. So the longer your member is effectively, the weaker it is.
Yeah.
Any questions? Oh yeah, that's the only step that changes, basically. Everything else for compression design is the same. It's just finding KE was really aids.
Today.
Yeah, but it's one of the most important parts of the last topic in this course, beam columns. That's why we're teaching it now, because the thing is about beam columns is there's more steps than what you've seen.
What's a beam column?
A beam column is you're basically doing a column design in full. Like, so you have like a frame, and then you need to design, let's say, this column or some shit. You need to check it in compression using gamma method because it's part of a big frame system, in bending, and in combined bending and compression.
Oh.
Yeah. And bending sometimes includes shear.
Okay.
Because in the actually, there's a good time to whip out the standards, right?
Can you go through shear in this course?
We do. There's if you look at my tags here, there's basically a section in the standards on bending. Here it says shear because I put it down anyway, but it's bending, compression, and tension. That's how the standards are broken up. Shear for steel is only ever flexural shear.
Okay.
The main thing that's happening is the bending, and the shear design you do is like a subset of the bending. Does that make sense?
Okay.
Whereas in concrete, there's actually two types. We don't cover the second type in concrete, because concrete you have slabs, you have punching shear basically. We don't talk about punching shear in the course, but in advanced concrete you do punching shear. My point is, steel, you only have flexural shear. Okay, that'll make more sense when I talk about shear. Anyway, sorry, I'm fucking digressing so much. I might not even have time to run through everything I wanted to. I might have to do it in like a... Yeah, I mean, we can go through it quickly because this might help you with your assignment. So I've got two examples for you. One's a custom shape compression. That probably won't help you guys too much, right? This is just how to find KF for a custom shape. So here I've got some kind of like heavily welded plate beam thing, right? Well, we call it like a beam girder wrap. And then like Yeah, basically just calculating KF. That's like the whole question. And then in the end, it looks like this, right? So remember what the blue and the red meant?
Effective area versus ineffective area.
Yeah, so in this particular example, would KF equal 1 or less than 1?
It would. Well, where's it's not? Is it a swing or?
Oh, we don't care about that yet, because that's the next step. That's like member effects. This is just the section we care about.
It wouldn't equal 1 because some of it is ineffective.
Exactly, yeah. It would to repeat in the recording, because my microphone on this computer is less sensitive than my microphone on my other laptop. Kane said is it would be less than 1 because some of it's ineffective. As soon as some of it's ineffective, KF is less than 1. Okay? And then, yeah, section capacity. Okay, that was the first question. The second question here, this is involving the gamma method, and it's a more whole idea of what you would see for compression design, right? Because usually compression design is not governed by the section capacity, it's governed by the entire member's bending buckling capacity, right? Anyway, it just says in the question, we're designing D3, okay? And I believe they give you the external force on it already.
Oh jeez.
Anyway, oh no, sorry, it doesn't say N star. All it says in this question is find what NS and NC are. So we don't care about the capacity equation in this particular example, right? It's just like, okay, design this member. Oh, sorry, not design this member. We will give you what it is on one steel, just find its capacity. And then NC is your function of effective length and stuff like that. And it's also the length, right? Okay, cool. So for the columns, we've listed out the major and minor axis resistance, right? Why is that going to matter, do you reckon?
Because you need to consider both the minor and the major axis.
Because we care about NC, like the buckling, right?
Yeah.
Yep. In this case, because we don't have that intermediate restraint in the middle, do you think it's going to buckle in the minor or major axis more likely?
The minor axis.
Yeah, exactly. Okay. Anyway, so this is just chucking numbers into the gamma method. You can look at this more closely when you're actually doing the questions for it in beam columns, because this is going to go over your head right now. And then beta E came from that table of values. Everything else comes from one steel, basically, right? Okay, so if we have a gamma B, the bottom, as rigid and as 0.6, and then we have a gamma T of 1.3, right? And we have a sway frame. What we do is we go to our table, right? And we look. So it doesn't matter whether. So gamma T and gamma B can be either axis essentially, right? You just start from one side and go to the other. We have two different values here because of our major and minor axis, and how K is like, how gamma was slightly different based on both the directions. You find the modified slenderness ratio and you find the max of it, and then that's how you get NS. Oh, sorry. That's how you, well, like, we basically just found NS with a separate equation. So once we find NS, alpha B is from that table, and then alpha C is from this graph. Okay, I think we're about done, guys. Do we have any questions? Let's see. Compression.
Wait, so when we do our like initial compression design,
Mhm.
when we choose, so let's say like they don't give us, they like we get given like a question where like we have a maximum compression member, right?
Wait, say that again. Sorry.
So let's say like we get a question where like we have to solve a truss and then there's like a
Yep.
maximum compression member.
Yep.
Except there's nothing like in the formula that lets us predict which net gross area is the best to use. So how do you guess effectively? Like,
Oh, it depends on the length pretty much, right? And what you're using. So, are you talking about your assignment?
kind of.
Okay, yeah, fair enough.
Yeah.
So,
Yeah.
back to your assignment. You have this truss, right? You have this truss,
Yeah.
and then it had this, and then so this member was in compression, right? essentially compression is like it's being compressed on both sides. You have this length, right? L is
I think about 4.
okay. Let's say it's 4 meters. That that alongside the information that you're choosing to use a UB is enough information for your initial sizing, right? Let's put a box there. Right. What number would you put in this box?
Well, I guess it would be like 0.6 or 0.7.
Yeah. Yeah, that's fine. Yeah, because if the length is like 6 meters, probably use like 0.5 or something.
So when you were saying like that they would want us to do it by hand though, like, did you mean like that we would have to try different lengths and then say like, oh, we're using 0.6 because it's this length, or like we're using 0.9 because like
Oh,
what we should assume.
no, you never have to justify why you do it.
So then what you said something about like they wanted you to do it by hand earlier.
What do you mean by hand, sir?
I
What do
think-
you mean by hand?
Yeah, I think you said like, oh, if you want to use 0.5, then you can't just like say from this like it's from the standards. Like you have to.
Oh, because it's not in the standard. So it's based on vibes, basically. When I say by hand, all I'm saying is you have to carry through every step. What I'm saying by not doing something by hand means you go off of a table.
Like there should be reasoning behind your steps, where in this case the reasoning is the table. But when doing it by hand is reasoning.
But like when you
all
use it,
through.
isn't that like what you're using the table for though, to get the initial sizing?
This table?
Yeah.
We're not supposed
No,
to-
you're not supposed to use this table. This table's a cheat. I'm just telling you this
So
so
we
you
use
get a
this-
better idea.
Is this
of-
not on one steel?
No.
No,
No, this is the.
Oh!
this is from the Little Red Book, bro. This is the hack book. Design capacity tables for structural steel. This is what I use at work. This isn't available online normally. This is like parroted, I'm pretty sure.
Oh, so like when we're actually like designing it initially, then we should use 0.9 as factor and then just guess 0.6.
For that specific case that I showed you, yeah. Or like for your for this
So
specific.
my understanding is usually you just guess around a number, right? There's no way. But because we have
It's
the
based
book,
on feelings. That's the thing.
because we have the book, we can
Yeah.
reverse engineer what
Yes.
the find factor should have
Yes.
been from the book.
So what you're doing is you're doing the right answer first.
Yeah.
And then you're going back and putting something beforehand, being like, oh,
Yes.
0.9 won't work because it
But then you
sucks.
didn't say you say, let's try 0.5.
Yeah.
Really?
Yeah.
That's why I pulled a number out of my ass because it's literally just based on experience.
But
I'm
then-
doing it
then
enough,
how-
and you'll know the
Then how
number.
will the marker know that we knew?
They don't.
They don't.
Because then
They
you
don't
gotta
know.
check it after.
He is made the
So,
right
would you write like,
So-
0.9 won't work, so let's switch it out with
You don't- you don't-
0.6.
There is a logic behind it though. That's the thing. It's just whether like how accurate your guess is, because it can only be 0.9 or less than 0.9, right? And it's how conservative you want to go is the lower it gets. So if you go 0.1, it'll be quite conservative. That's why if you're doing like fucking 11, 12 meter spans or something.
Okay.
Yeah.
I have a question back to the frames.
Yeah.
The formula for finding gamma,
Mhm.
I'm gonna need you to explain it again.
Okay.
The sum of what? Is it just all the beams connected?
Oh,
to that point?
actually, it's better.
Yeah.
That's why I have the
I
example
think
here.
it's
It's
like,
better.
I think it's like if it's gamma top, then like all the beams, all the sum of that, like in the bottom
Yep,
part of the
yep, that's
fraction is all the horizontal members connected to the.
Okay.
Exactly.
Let's do it again. Can we do east west again?
Yeah, this is east west, right?
Okay. So
So-
there's two columns.
So do you get gamma B, the bottom? Locking?
Nah.
So 0.6. So if it's connected to the ground at the bottom, it can only ever be 0.6 or
Or
10.
10.
Oh, you just didn't bother doing the cap.
No. That's the hard rule in standards.
Oh, that's hard rule. You can't
If-
do the cap.
Yes. If it's a footing, which means it's connected to the ground. If it's
Yeah.
rigid, it's always 0.6.
Okay.
If it's pinned, it's
It's-
always 10.
10.
Now the top is not connected to the ground.
Mm-hmm.
And here's where we use the formula. So sum means for each column, right? And we're
Yeah.
talking about the column itself and the column above it.
The left, top, and the bottom.
So
Yeah.
everything touching this node here.
Yeah, everything touches
So,
it. Okay,
so do
okay.
braces, are braces classified as beams in this?
No.
in this equation?
Braces are never structural. They're purely so they are structural, but like they're for this calculation, braces are not like one of the nodes.
So it's
coming off of
only
it.
like nodes in the cardinal directions.
Yes.
Okay.
Yeah.
So there can realistically only be 4 at a time.
Yes.
Okay.
Unless you're. Yes.
like at most
Yes.
4. At most 4.
Yes.
At a time.
So if we're doing the very top column, there'd be no column over, right?
Yeah.
Or if we're doing the very edge column, there'd be no beam on that side.
Yeah.
Yes.
Alright. Yeah.
And do you guys get like beta E and how it's 0 here and then 1 there? That just comes from the table. If it's yeah, there's like rules. There's like a niche rule where it's like if it's pinned on the side, then beta E is 0 or something.
Because it's
You'll get a feel for it once you do the questions.
fair enough.
But yeah.
Crazy.
Okay. Any other questions?
Stop the recording.
Okay, we're done.